In this video, we are going to talk about a special case involving the sine law. So in the previous video, we talked about the scenarios we use a sine law. We talked about angle, side angle, angle, and side angle. Now, when we are given side angle, there's actually a name for that situation. When you're given side angle, we call that the ambiguous case. The reason why we call it the ambiguous case is because when you have side angle, interesting things can happen. You can actually take the given information and you can potentially build two totally different triangles. Okay. Now at the same time, you can build zero triangles as well. You can build zero triangles, one triangle, or two triangles. Now, two triangles, personally, I find that the most interesting, but we're going to explore all the different cases, okay? So when you're given side angle, once again, you can build 0, 1, or 2 triangles with a given set of information. So what we're going to do is look at Geogebra applet, and then we'll come back to the lesson. So we will study the applet, the Geogebra applet, in order to better understand the ambiguous case. Now remember, the ambiguous case only occurs when you have side angle. And I also want to mention that I didn't make this Geogebra applet, so I want to thank whoever the author is. It's a very nice applet. It shows the ambiguous case very nicely. So when you are given side angle, you have to be very wary. You can build 0 triangles, 1 triangle, or 2 triangles. Now wait a minute, that sounds very confusing. How do you build 0 triangles? Well, that means given the side angle, it's impossible to build a triangle. And we're going to look at how that's possible. And then you can also build 2 unique or different looking triangles given side angle. So you know what, let's take a look. Right now I have the length of side A is 6 units, angle A is 30 degrees, and side B is 20 units. So based on the given conditions here, we actually, well, hopefully you can see that you can't possibly build a triangle, okay? With those values, you can't build up a triangle because side A is too short. So what we need to do is lengthen side A. And I don't want to spoil it, but you have to lengthen it such that it's equal to the height of the triangle. So it's just long enough. Okay, so you can think about this similar to what you learned in grade 10, like the shortest distance, right? So this length, let's say side A. Side A is going to be perpendicular to AB, okay? And you can, if you lengthen it just enough, let's go, you can build a triangle. And not any triangle, you can build a right triangle, okay? Like I said, you can think back to your knowledge of shortest distance to help you out. So it's just long enough, okay? If it's, let's go back a second. Oops, oh no. But if it's too short, you cannot possibly build a triangle. So in order to achieve one triangle, you need to be just long enough. And you can calculate how long it needs to be by using the sine ratio, right? So opposite over hypotenuse. So you can solve for what is the height of the triangle using AB as the base, and that is the minimum length in order for you to build one triangle. And of course, if you build that one triangle, it'll be a right triangle. Okay, so this is a very exciting part. I spoiled it a little. But if I lengthen side A just a little, we are going to build 2 triangles. What? Now, let's take a look here. So, the 2 triangles are triangle ABC and triangle ADC. Believe it or not, they both have a length of, for side A, they both have a length of 11 units. Side B is still 20 units, and angle A is 30 degrees. So you can build two very, very different triangles. Triangle ADC is an obtuse triangle, and triangle ABC is an acute triangle. And that's why you gotta be very careful when you have side-side angle. That is the ambiguous case. You can potentially build two triangles. So what I'm going to do is show you the circle because the circle will help us understand the ambiguous case better. So if you can imagine side A, let's go back, side A being the radius of the circle centered at point C. If it's too short, if the radius is too short, then you can't build the triangle. But if it's equal, if the radius of the circle is equal to the height, then you can build the right triangle. And if the radius is greater than the height of the triangle, then you can build two triangles. Now be careful though, there is a limitation. You can't have it to be too long because if it's greater than the length of side B, guess what? Okay, so right now you see you still have two triangles, but if it's equal to the length of side B, then you can build an isosceles triangle and that's it. You cannot build two different triangles. Okay, so even if it's greater, so if it's equal to or greater than side B, you can see you can only build one triangle. So I know this is a little tricky to imagine, but I think of the radius as like a door, and I'm swinging it across in order to build the obtuse triangle, in this case, triangle ADC. So that's basically an ambiguous case. You can imagine side A as the radius, so too short, no triangle, just right, gives you a right triangle, and if it's greater than the height of the triangle, but less than side B, then you can build two triangles. So one more time, if side A is greater than the height, but less than side B, then you can build two triangles. That's your ambiguous case.
Okay, so hopefully you found that little animation useful. And we're going to basically go through the animation together, but on a piece of paper, not as interesting or not as fancy. So this is what you basically saw in the applet. So the first scenario is when side A was too short, okay? We cannot build a triangle because the side A is too short. We are going to increase A such that we are capable of building a triangle. Now I want to mention A, or side A, is also the radius of the circle centered at C. Now, if you lengthen A, then you will be able to build a triangle. If we do so, we will have, and not any triangle, we will have a right triangle. Okay, so we go from diagram 1 to diagram 2. See, it's just long enough and you can build a right triangle. Perfect. So we lengthened, increased the length of A, and now have a right triangle. If we continue to increase the length of the radius of the circle, we will be able to build two triangles. All right. So let's take a look. Beautiful. See, you can build two triangles. One of them, triangle ADC, is an obtuse triangle, and triangle ABC, that's an acute triangle. So you can build two triangles. One of them is going to be obtuse, and one of them is going to be acute. And I want to mention that this triangle here, CDB, triangle CDB, it's an isosceles triangle, which makes sense because remember what we said in the animation? You swing side A over, right? It's like a swinging door. And if you swing side A over, you're going to build your obtuse triangle. Now, since you're swinging the side, that means it's the same length, right? If this is 12, then it's going to be, if CB is 12, then CD is also going to be 12. And that's the radius of the circle centered at C. So, of course, that makes perfect sense that triangle CDB is an isosceles triangle. Now, because triangle CDB is isosceles, whatever this angle here is at B is going to be, so angle CBD, that angle is going to be congruent to angle CDB, which means angle ADC and angle CDB, these two angles here are going to be supplementary. Okay, that's going to come in handy later on when we do the math. Okay, so let's go back here. When we increase the length of A, once again, we now can build two unique or different triangles. Now, if we continue to lengthen A such that A is greater than or equal to B, we will be able to build just one triangle, okay? So you can, if your objective, if your goal is to build two triangles, you have to have A to be longer than the height, but at the same time shorter than side B. Okay, so in this case, we lengthen A such that A is greater than B. You know what? We're going to have A is greater than or equal to B. Okay, now in the picture, A is greater than B, but even if A was equal to B, let's say A was 20 units long, you'll be able to build only one triangle, and the triangle will be an isosceles triangle. All right. So let us answer our initial question. It is possible to build two different triangles with a given set of information when... Okay, so the first thing is when you have the ambiguous case. And what is the ambiguous case? Side-side angle. When you have side-side angle, you have the ambiguous case. Now, like I said before, just because you have side-side angle doesn't mean you're going to build two triangles for sure, okay? So not only do you have side-side angle, you also need, based on the information before, you need, let's see, side A, it has to be longer than the height, okay? Side A has to be longer than B sine A. Okay, which is the height if you're using AB as the base of the triangle. So B sine A, right? If A is less than B sine A, if A is less than the height, guess what? You can't even build a single triangle. So you want A to be greater than B sine A, but hold on a minute, you don't want it to be too long. You want it to be longer than B sine A, but at the same time, you want it shorter than side B. So it's just in the perfect range where you can build two triangles. So first, if you have side-side angle, you may be building two triangles. Then you have to do the math. You have to check, is A in between B sine A and B? If that's the case, you can certainly solve two triangles, okay? So please don't assume you're going to build two triangles once you have side-side angle, once you have the ambiguous case, because you know what? You may be able to build 0 or 1 triangle, right? So don't make any assumptions. You have to do the math and you'll find it. All right. So let's do the math. Okay. So for triangle ABC, angle A is 30 degrees, A is 8 centimeters, and B is 10. So you know what? Let's draw that diagram here. Triangle ABC. So, let's see, 30 degrees for angle A. A is 8 centimeters and C is 10 centimeters. Okay. So, you know what? I'm a little wary now. The 8 centimeters is less than 10, but I have to ask myself, is side A greater than the height? Okay, it's already less than 10, but is it greater than the height? So we're going to calculate, let's draw this as, we know this is B sine A, but I'm going to label as H, okay? We're going to use AB as the base of the triangle, which means this here, CD, is the height of the triangle. Okay, moment of truth. Can I build two triangles? So that's 10 sine 30 degrees, and sine 30 degrees is half. That's one of our special angles, which is 10 times half. 10 times half is 5. Oh, so since A is greater than the height, but less than side B, therefore, two possible triangles. Okay, we can draw two very, very different looking triangles. We can draw an obtuse triangle with this set of information, or we can draw an acute triangle. So there are two different ways to solve for the different values of side C. Okay, we know there are going to be two different values that are possible for side C. Now there's a secret little shortcut I'm going to show you, but before I show the shortcut, I'll show you the long way, okay, which most people use. The textbook uses as well, but there is most certainly a secret shortcut. Now before I show you the long way, I'm just going to, okay, there we go. So triangle ABC could look like that, or triangle ABC like that. In fact, some people like to do this, like a subscript of 1 and a subscript of 2, to show you the two possibilities. But nonetheless, what we're going to do is solve for the two angles. Oh, sorry, the two possible sides for C, two possible lengths for side C. All right, so there's really not much you can do at the moment but solve for angle B. So we have sine of B over 10, which equals sine of 30 degrees over 8. So if you rearrange that, you're going to be taking inverse sine of 10 sine 30 degrees over 8. Not very pretty. Let's try that again. 10 sine 30 degrees over 8. Okay. So now there are two different triangles. Remember, there's an acute triangle. There's an acute triangle. And there's going to be an obtuse triangle. Okay, so if it's an acute triangle, angle B is equal, let's say we're going to say rounded to 2 decimal places. Angle B will be about 38.68 degrees. Okay. Now, if it's an obtuse triangle, remember what we said on the other page? We said that the angles will be supplementary, right? So angle B sub 1C, that angle will be supplementary to 38.68 degrees. Okay. So we do 180 minus, and which makes perfect sense based on the cast rule. Remember, sine is positive in the first and second quadrant. So you can get the exact same ratio using the second quadrant angle. Oops, okay, 141.32 degrees. Beautiful. Now that I have angle B, I can solve for angle C. How do I do that? You have two of the three angles, so you can solve for the third angle. So 180 degrees minus 30 degrees minus angle B. And then this one, same idea. So angle C equals 180 degrees minus 30 degrees minus angle B. Now, to be honest with you, I'm not very interested with angle C, but I'll find it nonetheless. Okay, I'll find it nonetheless. So 8.68 degrees we're looking at. And for the acute triangle, hold on, I'm just going to take 10 10 sine 30 divided by 8 inverse sine. Okay, and I'm getting 180 minus 30 minus. So it's 111.32 degrees. All right, so now we're in business. Now we can solve for side z, the two possible values for side z. So side c over sine of 111.32 degrees equals, let's do 8 over sine 30 degrees. So doing the math, c is 14.991. All right, and then here, c over sine of 8.68 degrees, which equals 8 over sine 30. So the reason why I start from the beginning, I have to recalculate angle B and then recalculate angle C because I'm trying to keep the answer as perfect as possible. So 10 sine 30 degrees divided by 8, inverse sine, take the supplementary angle. So I'm redoing the calculation. So I get my 8.68, but it was 8.68 blah, 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 blah. It was going a lot further than just 8.68. So I want to carry all these digits over so I can get the most accurate possible value for side C. There we go. So C is approximately 2.42 centimeters. Okay, therefore, C is approximately 14.91 centimeters, or C is approximately 2.42 centimeters. Okay, it depends on whether you have the obtuse triangle or the acute triangle. So this is perfect. It lays it out very nicely. Angle B could be 38.68 degrees, or it could be 141.32 degrees. Angle C could be 111.32 degrees, or it can be 8.68 degrees. Huge difference. And of course, we already mentioned the two possible values for side C. I want to show you the shortcut, but if they're asking you to solve triangle ABC, then there is no shortcut. When they ask you to solve triangle ABC, you have to show them the two possible values for angle B, the two possible values for angle C, and the two possible values for side C. Okay, and there's no shortcut for that, at least not that I know of. But if they're only asking you for the length of side C, then yes, there is a shortcut. So I'm going to do the exact same question on the back side of this sheet. Okay, so I just hopefully remember the numbers here. So I'm going to draw the diagram has to be very nice. I'll try my best to make it a big diagram here. So this was A, this was B here, and this was C. So this shortcut really depends on your understanding of the ambiguous case. So I'm not going to show you again that it is possible to draw two different triangles using the information. What was this? This was 10, I think. Okay, and this was 8. And yeah, okay, let's go. Let me just triple check real quick. Yeah, all right, perfect. So let's see here. This is the height. So I'm going to let CD be H. All right, and I'll call this E. All right. So side C is equal to AE or AB. So really take your time and appreciate that. Side C can be AE or AB. If side C can be AE or AB, that is very useful. So C equals AE or C equals AB. That is going to be the basis of our shortcut. Now, we can actually find the length of AE and AB without doing all the work we did previously. How can you find AE? If you look at the diagram, AE can be found using AD minus AD minus ED. AD minus ED. So let's write that down. AE is AD minus ED. Now, what about AB? AB, you can write it as AD plus DB. AD plus DB, right? AD, DB, and that gives you AB. So far, nothing mind-blowing, hopefully. But this part is a little interesting. ED, okay, if you look at the diagram, I didn't do a very nice job, but ED, that length of ED is the same as the length of DB, because when you have an isosceles triangle and CD is the altitude, it's also, the altitude is also the median when you have an isosceles triangle, and triangle EBC is most definitely an isosceles triangle. So that's a grade 10 thing. In fact, you also talked about this in grade 9, but hopefully you can imagine that ED is the same length as DB. So instead of writing ED and DB, I'm going to change one of them to, you know what, let's change DB to ED, okay? Because DB is equal to AD. So AD plus DE, because DB is the same as ED. I'll write it as ED instead of ED. ED. Okay. And this is the easy part. AD, I can find the length of AD easily. AD, Pythagorean theorem. AD is Pythagorean theorem, right? You want this leg of the right triangle ADC. You want to solve for length of the leg. So it's going to be 10 squared minus h squared. And what about ED? ED, no way. Pythagorean theorem again. Because if you look at triangle CED, that's a right triangle. So ED, 8 squared minus, and that's what makes this shortcut so beautiful. You do 2 Pythagorean theorem calculations, bam, you're done. Now there is one little step that you have to do before all this, before the 2 Pythagorean theorem steps, you have to solve for the height. Okay, so h is equal to, we solved for the earlier, but it was 10 sine 30 degrees, which is 5. All right, so you know what? I'm gonna punch it all in my calculator. So let's do AD. So that's 100 minus 25. And then let's do minus 64 minus 25. 2.4. Wait a minute. That looks very familiar there. All right, and then this one. So it's going to be root of 100 minus 25 plus the root of 100 minus, oops, it's 64. 64 minus 25. Oh, let's try that again. 100 minus 25 plus the square root of 64 minus, wait a minute, 14.91. 2.42 centimeters, 14.91 centimeters. You can't see it. 2.42, 14.91. Beautiful. So, you know what? You want to really focus on this. How will we solve for the 2 possible lengths for side C? You did I guess you can say you can solve for the height using the sine ratio, which you have to do anyways, no matter which way you're going to go, no matter which way you choose to do the question, the method before or this method. So that's a tie, I guess you can say. Now, calculating length of AD should take a very short amount of time, as well as ED. So this method to me is like a clear win. But you know what? Sadly, even though I teach this method to a lot of students, they still prefer the sine law method. So you know what? I'm not going to force you to use this method. It's absolutely up to you. But this to me is very beautiful. Okay, so that's the ambiguous case. So whenever you see side-side angle, be very careful. Take a step, take a breather, and slow down.